in our experiment, which involved a solution that had potassium thiocyanate mixed with iron 3 chloride, so this blood red colour, we had this dynamic equilibrium in place. We have the forward reaction occurring at the same rate as the reverse reaction until we added something to it. So we added this stuff into some different petri dishes and added some different chemicals to it and observed a change in the depth of the colour of the solution. It either got lighter or it got darker. What we were showing was a thing called Le Chatelier's principle. And Le Chatelier's principle explains that an equilibrium can shift its position, which means change the concentration of reactants or products, when we try to affect it, so when we affect change. We can affect change by making it hotter, making it colder, adding a reagent, adding a product, or removing a reagent, or removing a product. And these were the things that you did. So one of the things that we did was to add some iron ions in the form of iron 3 nitrate. While iron 3 nitrate was never used to make this equilibrium system in the first place, we added iron 3 nitrate, which added iron 3 ions. By increasing the concentration of this, the equilibrium will shift. We say that it shifts to minimise or undo the change that we have caused to it. So if I increase the concentration of this one, the forward reaction will be favoured, which will make it get darker because it will have to increase the concentration of iron thiocyanate complex ion, this one here. And because this is blood red in colour, it got darker and darker and darker. For some of you it went nearly black. It added so much that it went nearly black. What didn't work quite so well, but should have had a similar impact, was to add more potassium thiocyanate, which adds more thiocyanate ions. Once that crystal dissolved, it had to dissolve first, okay? Once it dissolved, it should have started to favour the forward reaction, to undo that increase in concentration of thiocyanate ions by making more of this. And so therefore, again, it should have got a little bit darker. The reason it wasn't so dramatic for yours is it wasn't dissolving very well. Okay, it was already a relatively concentrated solution. The last thing that we did is to add a chemical called sodium fluoride. Now, sodium fluoride will actually remove iron 3 plus ions completely. It'll take them out of solution into a precipitate, so it'll take them away. It'll bind with them. And so if this thing is starting to drop in concentration, what we say is that it favours the reverse reaction. So what you should have noticed is that the colour got pale. And most of you I observed, added lots and lots and lots of it, and it ended up going colourless with a white solid sitting in there. And so what you'd end up doing is reversing it so much that you broke the equilibrium, because it reversed so much that in the end, all of the iron from here and here was being drawn out, first of all this way, by the reaction being reversed, and then being precipitated out by the fluoride ions. So you ended up completely removing the iron, 3+, so you ended up with just a solution that was basically sodium ions, potassium ions, and thiocyanate ions. So you completely removed it. The Chatelier's principle, though, the way to apply it for what you did before it fully decolorised, was to say that you removed some of the iron 3+ by using sodium fluoride, which favoured the reverse reaction to try to recover some of that concentration, to bring it back up, and in doing so it reduced the concentration of this complex ion, which should have made the blood red colour fade. Okay. So what happened in there? You changed the concentration of all of those species, by the way, because when you make more of this, the concentration of so when you go backwards, the thiocyanate concentration must have gone up. Now, thiocyanate's colourless in this case. It's only coloured when we put it in here. So you've changed all of these. This dropped. We were trying to get it back, but we never did. This goes up, and this goes down. So all of them changed. So what we say is that a new dynamic equilibrium was established. Okay, so it's not the same anymore. You've actually changed it. And in your case, you broke it, which is fine. That's one of the things we can do. We can drive an equilibrium so far that we end up completely removing one of the species. And that's actually really useful in industrial equilibria, because that's how we collect one of the products and drive the equilibrium the way we want it to without wasting a lot of energy, so heat and electricity. So today we've looked at what is a dynamic equilibrium, what are these reversible reactions, what is a dynamic system, so it's where the rate of reaction is equal for the forward direction and reverse. Then, can we mess with that equilibrium? Yes, we can, and it's governed by some rules called Le Chatelier's principle. Anything you do to it, it will try to undo it. So if I heat it up, it would actually end up going in the endothermic direction to try to cool it down, for example. If I put it under ice, or put ice under it, then it will try to go in the exothermic reaction to heat itself up again. If I add one of the reagents, it will favour the forward direction or forward reaction to reduce the concentration of those reactants. And tomorrow we're going to look at a gas system, which is also a solution. Gases can be solutions. A gas system where we're going to look at the effect that pressure can have on an equilibrium system. Any questions?